three talks on multi-level Monte Carlo. So for those of you who weren't there on Monday, I summarized multi-level Monte Carlo and the work that we've been doing in that area, myself, mostly with AJ, some stuff independently with Tempone and Hole, and I summarized the three general strategies for applying multi-level Monte Carlo in an inverse problems context, and then I went into some detail on about two of the methods that we've worked on with AJ, and one of those methods was multi-level sequential Monte Carlo, which was what we called an importance sampling strategy. Then we looked at multi-level particle filters, where we used what we call a coupled algorithm strategy, and this is an example of the last type of strategy, which we call approximate coupling strategy. So we're going to look at Bayesian static parameter estimation using multi-level Monte Carlo. In fact, I also spoke about this multi-level ensemble common filter on Monday. So, in fact, I said on Monday that was the last time I was going to introduce multi-level Monte Carlo, but I went ahead and put it in here because I expected that there might be people here that might be different crowds, so that there might be people here today who weren't there on Monday. But I'm going to try to go. I'm going to try to go through that rather quickly. A lot of people saw that already on Monday, and/or Wednesday at NUS when Maddie introduced it in the context of randomized multi-level Monte Carlo. All right. So what are we talking about here? The aim is to approximate posterior expectations of the state path and static parameters associated to a discretely observed diffusion, which must be finitely approximated. So I emphasized this in the talk on Monday as well. So the issue that we're focusing on here is the fact that we can't actually solve the diffusion that we want to solve from. We can't even simulate a single sample from it. So we're aiming to simultaneously take into account the discretization bias from discretizing that infinite, that continuous time process with the sampling error. So we're going to apply an approximate coupling strategy, so we can use multi-level Monte Carlo together with a particle marginal metropolis Hastings algorithm. So this is this Beaumont paper in 2002, which proposed this idea of doing a pseudo-marginal, of using a pseudo-marginal method. That's the Andrio Roberts 2008, and this paper with Christoph and Arno on the P particle MCMC, which we've seen a lot about so far already this week and last week. So multi-level Monte Carlo methods, they reduce the cost to obtain a total error tolerance, including the statistical approximation error and the any other approximation error to a level of epsilon. The method was introduced by Heinrich in 2000, and then it was popularized. There wasn't very much work in between 2000 and 2008 when Mike Giles had this paper where he used this multi-level Monte Carlo to estimate option pricing. So recently this methodology, and this is, say, since 2013, has been applied to inference problems, and that's mostly in the context where the target can be evaluated up to a normalizing constant. So this is Huang is at NTU here in Singapore. Stuart Schwab, they had this idea of using this as so-called importance sampling strategy to apply MLMC to Markov chain Monte Carlo. Dodwell, Kettleson, Scheichel, Teckentrup in 2015 proposed a different method for applying MLMC to MCMC. This is an early paper by myself with Tempone and Hole on multi-level ensemble common filter. And here is multi-level sequential Monte Carlo samplers paper with Beskos, AJ, and Tempone, and Yan Zhu. So here in this context, we can't evaluate actually the target. We can only simulate from the dynamics. So the prior we can only simulate from, but we can evaluate the likelihood. But by using particle marginal metropolis Hastings, we're able to sample consistently from an approximate coupling of successive targets, and thereby we then correct this estimate we get with respect to the approximate coupling for the final estimator. So this is with, again, with Kengo, AJ, and with Yanju, just published in CISC. All right, so just to review briefly multi-level Monte Carlo. So the canonical example coming from this Giles 2008 paper is the estimation of an expectation of the solution of an intractable stochastic differential equation. So so this equation's well-defined, well-posed for a wide class of f and sigma, but only for very few f and sigma can we actually sample from the solution at the final time. And we want to estimate expectations of some function of the solution at the final time. So what we typically do is we have these two levels of approximation. So we introduce some discretization resolution parameter h, and then this is what's called Euler-Maruyama iteration. So it's just Euler method for the drift part, and then one approximates this this Brownian increment in this fashion here. So we draw some NT standard normals. We iterate this recursion, and that gives us one sample. And then in order to approximate this, we need some n of those samples. So to slightly abstract that, so we want to approximate expectations with respect to this limiting infinitesimal distribution of some function g. And so the standard sort of naive approach is you discretize the space. That gives you an approximate distribution for a given resolution, say e to L, which is, say, discretized with a parameter HL. Then we take some NL number of samples, and we construct the unbiased estimate of the expectation like this. The mean square error is then equal to the variance and the bias. The variance is going to be of order of NL inverse, and then the bias is going to be determined by this HL parameter. And so that, so that HL parameter is then going to determine how many degrees of freedom we have in our approximation. That's going to determine the cost to obtain a single sample. And then we're going to need epsilon to the -2 number of samples in order to get a mean square error of epsilon squared. And so here, the thing that we're going to try to avoid with, or that we do successfully avoid with multi-level Monte Carlo, is this product of costs. So we have a maximal cost here multiplied by the required cost here. Now, since we have this limiting measure, it's reasonable to suppose that we might be able to introduce a hierarchy of discretization levels E to L, which are convergent. Okay, so with the decreasing step size, for example, in the estimation of the SDE. And then, so if we now define these increments as the difference between expectations with respect to successive measures with this convention here, then we have a telescopic sum like this. So expectation with respect to E to L is equal to this sum of these YL. And now each of these YL can be unbiasedly approximated for any pair in this form, and these pairs UL, UL minus 1I, these NL, ideally IID, random variables UL, UL minus 1I for each L, give us an unbiased estimate of the YL, right? And the point, the key point here is that actually these UL, UL minus 1 can be coupled, and in fact that's what we want. We want these guys to be coupled, and we want them to be coupled in some sort of optimal or maximal fashion. So to iterate that again, so we say so the multi-level Monte Carlo method proceeds like this. So we want to sample IID from some coupled measure e to bar that has the correct marginals e to L and e to L minus 1, and we're going to get some NL pairs like that for each level, And then we construct a multi-level estimator like this. So it's just now the sum of these estimators of the individual increments. And now we have an unbiased estimator again, so the mean square error now with respect to between the multi-level estimator and the limiting infinitesimal expectation is again a sum of the variance and bias, but now the variance again. Actually, maybe I forgot to mention that we're independent between levels here as well. And so the variance is a sum of the variances of the individual levels, and the variances of the individual levels now are going to be proportional to the limiting variance of the increment divided by NL. And so now these terms can be made, for example, these terms can be made constant by letting NL be proportional to VL. But in fact, we can do even better than that. So the bias is coming from the level L. And now if we minimize the cost as a function of the NL for a fixed variance, we find out that actually NL should be proportional to square root of VL divided by CL. And so the idea is that these VLs are decreasing as the CLs increase. Sorry, so the CL means cost of obtaining one pair at level L. And so we find out, if we do this simple optimization problem, that we should scale the number of samples at level L like square root of VL divided by CL in order to minimize the cost. Okay, so before making that statement rigorous, what is this coupled measure? So how do you do that? How do you couple these measures? So for an SDE, for example, you take two successive discretizations of the same. You take two successive discretizations of the same limiting Brownian motion, and you drive your SDE with those two approximations. So if we have here one pair of levels, we've got a level 1 and a level 0. We have some N1 standard normals that allows us to construct the Euler-Maruyama approximation of the SDE at this level 1. This would be the fine level of this pair of levels. And so this process here, if we sum that up, we have this Wiener process W1 in the green with the green curve here. And then we sum every second increment to drive the coarse process. And so then the coarse Wiener process is given by this blue curve here, which coincides with the fine process at every second, at every coarse discretization point. And so these guys stay close, and their variance stays close, and that closeness of the Wiener processes translates under mild regularity conditions on these coefficients to closeness of the variance of the process itself. So if we assume that HL is 2 to the minus L and we have alpha and beta bigger than zeta, so that we have weak error rate of HL to the alpha, so the absolute difference of expectations between the approximation and the limiting thing, and then a strong error, which is the square of the difference, expected value of the square of the difference between the approximation and the limit, with a rate of beta. Then, so this is going to give rise, this alpha will dictate the bias, the beta dictates the variance, and then we assume that we have a computational cost to obtain one realization at level L of HL to the minus zeta. So HL inverse is going to be roughly the number of degrees of freedom. So that's reasonable. In fact, for the SDE here, and for in almost any case with SDEs, zeta is 1, any case that I can think of. But in fact, you can extend this methodology to SPD or PD and things of that sort, and then you get different coefficients here. But you always sort of, depending on polynomially on, typically at least, depending polynomially on the number of degrees of freedom, so either linear, quadratic, or cubic, or whatever. So both cases are going to require, for both, if we do single level or multi-level, we're going to have the same bias, and so we're going to need to choose the final level to be proportional to log epsilon in order to get HL to the alpha to be order of epsilon. And that then in turn is going to let us represent the cost in terms of epsilon. And so we get a total complexity of, say, of epsilon minus theta over alpha minus 2, right? Because the cost per sample can be expressed, it's going to be proportional to this. And then fixing the variance at epsilon squared means number of samples is epsilon minus 2. And so the multi-level cost is, in turn, is going to look like this. And because of this assumption here, the relationship between the decay of the variance and the growth of the cost, we end up with a cost that's proportional to epsilon minus 2. And so the scaling, the complexity, ignoring constants altogether, is the same as simply IID estimating an expectation of some scalar random variable with IID draws. So, and for a Milstein solution of a SDE, we have a single level cost epsilon minus 3 and a multi-level of epsilon minus 2. Okay, and if the relationship between beta and zeta is different from this, then you end up with different costs, but always better than the limiting case. And sorry, just one more point is this is Cliff, Giles, Scheichel, Tekentrup, who are credited with first looking at this in the case where zeta is not 1. So just to give credit where credit's due. All right, so back then to parameter inference. So I spent longer than I planned to spend on that multi-level Monte Carlo. So hopefully people who haven't seen that are now feel that they're experts, and people who saw it already on Monday, well, are also now experts. All right, so for parameter inference, so the problem we're looking at here now is parameter inference, but you can see sort of how multi-level, you would want to use multi-level Monte Carlo in this context. So again, we want to estimate posterior expectation of a function phi of the joint path and parameters of a intractable SDE, so some SDE where, okay, for any value of theta, we cannot sample from x at capital T exactly. And now we want to condition on some noisy observations where we do know the likelihood of y given x. And we want to estimate now, so we want to estimate expectations of phi of theta and x, 0 to t, where y 1 to t, where this 1 to t notation has this meaning here. Sorry, I didn't define it explicitly for x, but same for x. Okay, so the hidden process is a Markov chain now between observation times. Say we have observations at unit times, but we cannot simulate exactly from that Markov chain, so we have to discretize. We discretize, say, with some resolution h, and then we denote the transition kernel by f theta for that given value of theta, f theta h. This thing can be simulated from, but its density cannot be evaluated. So this is quite well known to everybody here. Well, okay, so density could maybe be evaluated in principle, but you would have to integrate over all of the individual steps. So for a single discrete time step, you know the density, but then in order to get the density of the Markov kernel, you'd have to marginalize over all of the intermediate steps. So it's a bit, so that's a bit of a mess. We'd like to avoid that, so we're going to assume that we can just simulate from this for a given value of theta and h. And now the joint measure takes this form here, so it's going to be proportional to the prior on theta, prior on x0 given theta, and then this product of likelihood and transition terms. And so what we would like to do in order to apply the multi-level Monte Carlo identity, the multi-level Monte Carlo acceleration framework, we'd like to express the expectation of the joint at level L capital in terms of this sum of, in terms of a sum of increments where the SDE is solved at successive mesh refinement levels. So we'd like to do that, but we don't actually know how to construct, we don't know how to construct a coupling, an exact coupling, which admits this guy, well, this guy and this guy as its marginals. We don't know how to do that. But actually, we can construct an approximate coupling for which we can construct an approximate coupling such that the weights of the given marginals that we're after with respect to the approximate coupling are well behaved. Okay, so it suffices to consider a single pair, right? So we're going to have these L capital pairs, but we only need to look at a single pair. So consider a single pair for some h less than h prime, and we want to approximate this expectation here, this difference of expectations here with respect to pi h and pi h prime. So let z be xx prime, and so this will be some coarse state, if you want, and then some fine state x and some coarse state x prime, and let q theta hh prime denote a coupling of the transition kernels of the Euler-Maruyama with respect to h and h prime, right? So this is just another way to write. This is exactly what you use in the original Giles option pricing stuff, and that's the example that I show with the pictures of the coupled Wiener processes, right? GP, so we define then this is the guy that makes this approximate. So we define this capital GP theta to be the max of the G theta for the observation YP evaluated at x and x prime. And so then we have this approximate coupling of the filters at the coarse and fine. Here where we've got this Z process with these selection functions here, and nu theta now is the initial coupling. And I'll explain to you in the next slide. It will become clear why we would choose that. I mean, you can see, okay, well, it has some. Of course, the marginals are going to have something to do with the marginals, with the marginal filters that we're after, because we have the right selection functions in there. But now if we look at this, if we re-express this difference of expectations here in terms of expectations with respect to this approximate coupling, then we can characterize these in terms of these weights here, where now H1 and H2 are the weights of the fine filter with respect to the ratio of the fine filter density with respect to the approximate coupling and the coarse filter density with respect to the approximate coupling density. Where notice that those guys that we can't evaluate have dropped out. So that's convenient. So it's backwards compatible for the guys who saw the MLSMC on Monday. We can apply this strategy to the ones where we use the importance sampling, but we can't apply the importance sampling blindly to this problem. So I should mention, so these guys are bounded by 1, right? So that's the motivation for the choice of the sign of for the choice of form of the G capital. And let me also mention that we also have some recent work with Jordan and Matti, where we use this together with this approximate pseudo-marginal Metropolis Hastings with correction. And there we're calling this for the particle filtering context a delta particle filter, and we use actually different G, which also works here, which is average of the G's. So that also can work. Okay, so particle Markov chain Monte Carlo. I'm just going to talk about. Well, we're going to use a particle marginal Metropolis Hastings, and I think that there are a lot of people in the room who can explain this particle Markov chain Monte Carlo better than me. But here I've just got a couple of slides where I'll introduce that for people who aren't familiar. So if we introduce these additional parameters a, 0 to n minus 1, so each of the a sub I is between 1 and m, then we can write the bootstrap particle filter approximation of this guy in this form. So we can write down actually this, law of the particle filter on the paths, some m paths and some m weights, the weights associated to the resampling. So you resample it each time according to this, and then you evolve through the mutation kernel. This, of course, is Pierre's book, Feynman-Kax Interacting Particle Systems, 2004. Again, I probably should update to a more recent book, but the classics are classics, so we keep that there. So yeah, so this ZP minus 1, AI P minus 1 is resampled according to this probability. And I've actually realized subsequently, of course, everybody by now here who was here last week at least knows that there's a slightly better way or easier way to understand this stuff. But for now, so suppose that we draw J with probability proportional to the selection weights at the selection weights at the final time, and define the Z hat at time n to be that draw according to the weights at the final time, and then trace its ancestral lineage. So define Z hat n minus 1 like this, and recurse that. Okay, and define PM HH prime like this. So this guy is an unbiased estimator with respect to the given M particle filter. And then let epsilon denote an expectation with respect to all of the variables that went into this simulation. So those indices, the paths, and in that final index. And note then that the expectation with respect to the law of all these auxiliary variables of some function of this Z hat times the marginal likelihood is actually equal to the expectation with respect to the unnormalized, or sorry, integral of phi with respect to the unnormalized target. And so that, I guess, is my best effort to understand why actually you can run a Markov chain over theta using this unbiased, non-negative unbiased estimate of the target, and then you collect, you simply store up these Z hats for each theta I, and you end up getting and these guys in the end of the day are consistent with respect to the joint. Again, this is related to the pseudo-marginal. This is the Beaumont paper, Christoph and Gareth Roberts, Arnaud, Christoph and Hollenstein, 2010 paper. So the algorithm looks like this, the particle marginal Metropolis Hastings. And of course, this is not the only particle Markov chain Monte Carlo. There's this particle Gibbs, which is less easy to understand, actually, I would say. Okay, so it goes like this. So we sample theta 0 according to the prior. Then we sample these auxiliary we sample from a particle filter. So these weights and indices and paths from a particle filter. Then we store this unbiased non-negative estimator of the marginal likelihood. Then we select a path. So this I described on the previous slide. So we just trace the ancestral lineage of one of the paths. And that gives us our sample at time 0 from the PMMH, this theta 0, Z hat 0. Then we just run a Metropolis Hastings chain on theta, where at each step we simply do that thing again, and then we use this acceptance probability here. So we set theta I to be theta star, and then Z hat I to be Z hat star with this probability here. What I found most mysterious about this to begin with when I first saw this algorithm is that the z doesn't appear here at all, but the z's basically a function, for a given theta, z is a function of theta. So, so that sort of is a way to kind of understand that heuristically. Okay, so now from this PMMH, now we want to construct the increment estimator. And now again, remember this notation where z is equal to x prime. So we can construct a consistent estimator. Ultimately, we want to estimate this thing, which we can rewrite in terms of these weights. We can rewrite, in terms of expectations with respect to this approximate coupling. And now we have these samples from this approximate coupling from the PMMH, these theta I, z hat I. And so we simply construct that using these self-normalized importance sampling estimates. Okay, so that converges. And now we put that, so now we just put that into the multi-level, into a multi-level estimator. So the multi-level estimator is going to be the sum of these ELNLs. And so these ELNL is going to take this form here, where in order to avoid proliferation of notation, I have not included the L's on these samples, but of course you do that you do what we did, what I described in the previous slides for each level L. So we have for each level L we have something like this, and the number of samples at that level L is NL. So these theta I, z hat I are associated to a particular level L, and the z hat I is equal to x hat I, x hat prime I. Now, so each of these is a consistent estimator of the level L increment, and so so their sum then is a consistent estimator with, again, this convention of discarding the of defining the minus one, the measure h minus one as to be identically 0. This is now a consistent estimator of the expectation with respect to the level L capital approximation of the filter. Okay, so the thing, so there's sort of so the variance term in this estimate. So then we're going to have a bias term, and then we have a variance term, and the variance is going to be the expected value of this, guy here. I'm sorry, this is a sloppy slide. I should reorganize this slide. So we define this, but all the relevant information is there. So we have this E bar NL L is a centered increment. So you center that according to its limit. And in the end, we're going to have to look at this. So the bias, we're going to have a bias term associated to this, and then we have to consider this. And so that's where this is where all the trouble happens. This estimate of the L2 error of this guy here. So we've got independent levels, so this is exactly equal to the sum of the expectations of the individual levels. And so if we make these assumptions, I know that this is quite a strict assumption, but so these are not a minimal set of assumptions, but sufficient assumptions. So we assume that we have uniform boundedness below and above of these weights over all theta, x, and y. And then we assume that we have some rate with respect to the prior over both the path given the parameter and the parameter, which is of order beta, so h prime to the beta, where h prime is the coarse discretization parameter. And suppose that we have a strong mixing condition as well on the PMMH kernel, which we think of in terms of its as a metropolis Hastings on the extended state space. Then for all n we have a beta bigger than 0, so that for all bounded and Lipschitz phi, we have an estimate like this for this level L increment. So we get something like, we get a bound HL to the beta divided by NL. And beta, where beta is exactly this rate, which is the strong error rate of convergence of the process uniformly over all the over all parameters in this theta. And so if you were there on, if you saw the multi-level particle filter on Monday, you remember that actually we lost half the rate for that multi-level particle filter. And so we're quite pleased with that actually we get the correct strong rate of convergence there. So with the additional assumption that we have some scaling of the cost proportional to HL to the minus gamma, and we have a control on the bias of HL capital to the alpha, then we get this multi-level Monte Carlo theorem. So assuming that we have under those assumptions for these bounded Lipschitz functions, and for any epsilon positive, we can choose capital L and this schedule of NLs from L0 to capital L, so that we have this mean square error controlled by epsilon squared with a total cost of epsilon minus 2, or slightly larger if beta's not larger than gamma. Okay, so we looked at this algorithm on some examples, and indeed it works. Indeed, it works quite well. It gives the promised rate, and it seems to be quite efficient also. So we looked at OU process. So here we have this notation. This notation is used for a standard normal with mean m and variance tau squared, and then this notation is used for a gamma with shape parameter alpha and scale parameter beta. And we set these other parameters like this, and take 100 observations of this process with theta is 1 and sigma is 0.5. And now, so the unknowns, the parameters here are theta and sigma, actually. So I'm sorry about that. So what was theta for the whole talk is here theta and sigma. So you think that's theta 1 and theta 2. And for all the examples, we'll have a theta and a sigma, and that's the parameter. So a two-dimensional parameter, SD with some 100 observations in the OU case. Here for Langevin, we look at 1,000 observations. Pi is a probability density function of a student's t-distribution with theta degrees of freedom. So, excuse me, here we want to identify that the relevant number of degrees of freedom for this given series of observations. Here we take the observations to have this form. So this is relevant to, we can think of this as a model for log volatility, stochastic log volatility model. So here theta is 10, sigma's 1, and tau squared is 1. Okay, so those are the two examples we look at. Here, sigma is given by the red line and theta is given by the blue line, and this is an autocorrelation function for the two examples of the Langevin and the OU. So this is a typical PMCMC chain. This is what a typical PMCMC chain is looking like for this example. So you can see, I mean, well, it's quite good. So converges quite quickly, and so the cost versus MSE for the two parameters for the two SDs look like this. So this is multi-level with red, and multi-level PMCMC in red, and then PMCMC in blue. And so what we do is we look at various error tolerances, and we simulate both algorithms to obtain that error tolerance. And here the cost is on the y-axis, and it increases much faster for PMCMC. I believe it's the same that you would get for the SD example. So this is like error to the minus 3/2 think this is mean square error actually. So this will be error to the minus 3/2, and this would be just error inverse. And right, and so we fit the rates here. So for multi-level, we have basically very close to -1, and for the PMCMC, we get very close to -1.5. All right, so we apply this new approximate coupling strategy to in order to apply MLMC to PMCMC for static parameter estimation. That paper is published in SISC. We've also published a paper where we use that same approximate coupling strategy, but within a multi-index context for multi-index MCMC. I'm sorry I didn't say any details really about multi-index. So if you have more than one discretization direction, then it turns out that multi-level's typically not the best thing that you can do. You want to do something like multi-level independently in different directions. Sorry, that says in progress. That's incorrect. That's been submitted. That's a paper with Linda, who's here and who's here at NUS, but not here today. That's multi-index SMC squared. So we look at, okay, the process is not a SDE, it's a SPDE. And then we construct a sequential algorithm using this SMC squared method of Papaspiliopoulos et al. And Pierre Jacob. Papaspiliopoulos, Pierre Jacob, and Nicholas Chopin, I think, were the three authors on that paper. All right, so that's basically it. So if you know available people looking to do PhDs and postdocs who might be interested to come to Manchester, send them my contact information, because nobody here is probably looking for a PhD, but postdocs. Well, actually, what we have now, the opening now is for data science and machine learning with HPC for fusion applications. So it's sort of, I made the mistake before of not clarifying that, well, I don't actually have money to pay someone to do that kind of stuff at the moment. But there's money around to pay people to do that kind of stuff. And more will come. So these are the references. That's Heinrich, original multi-level Monte Carlo, the Giles multi-level Monte Carlo, the paper where they generalized to gamma not equal to 1. This are the pseudo-marginal papers, the Beaumont paper from genetics, Andrew Roberts from Annals of Stats, 2008. This particle MCMC paper of Christoph Arno and Hollenstein. This is a paper that I talked about, which is now in SISC. This paper where we apply the same approximate coupling method to a multi-index MCMC. That's an International Journal of Uncertainty Quantification. This, now I have the correct thing written there. That paper is submitted. It's on the archive. This is this multi-level SMC samplers, and these earlier multi-level MCMC papers. This is a recent ML ENKF where we look at SPDs, the original ML ENKF paper I mentioned before. This is a review paper where we try to summarize all of these algorithms within these three categories, these three strategies of importance sampling, coupling of algorithms, and approximate coupling. This is a paper with Pierre where we look at MLSMC samplers for normalizing constants. So I mentioned that on Monday as well. So we construct some different estimators than the MLSMC estimators there. And MLPF, this paper is in SciNum. So that's a multi-level particle filter where we lost half the rate. I talked about that on Monday. So we lost half the rate for the MLPF. We got it back here, but of course it's for parameter estimation, and we need to pay attention to the whole path. It's not really online, so it's gonna always, cost is always gonna grow with n. Here we applied this. We applied the forward an inverse UQ, I say. So okay, so what did we actually look at as we looked at the MLSMC and MLMC for these elliptic non-local equations. So those non-local equations are modeling things like anomalous diffusion, or they're used for modeling fracture dynamics. All right, so thank you. I didn't put everybody to sleep. This nice rainfall happening outside. And
Kody, can I ask you something about an assumption?
Please. Yeah.
You go back to you had a strong mixing assumption. Yeah.
Yes.
So what's n there?
N?
Yeah.
Oh, sorry. Yeah. So n. Oh, yeah. N is we're looking at paths of length n. So n's not to do with the MCMC. It's to do with the number of observations we're incorporating into the filter.
And K is
the kernel, so that's the PMMH kernel, but viewed as a measure over all the auxiliary variables, including the theta.
And where is the number of particles?
Sorry, I introduced this space without really specifying what is W. W is the thing which is going to be big M times, so if there are M particles in each filter, it's going to be, that whole space over well, I haven't written out what the full thing is, but it's over at least all of these. Sorry, it's that space W is the space of this plus theta. Yeah.
What type of particle product do you use for such a space?
We use exactly the one, this one. So we draw theta according to, so it's as though we were just doing Metropolis Hastings on theta, except here we replace the likelihood, the marginal likelihood, by this unbiased approximation of the marginal likelihood using M particles of a particle filter. And so those particle filters actually between steps we take as just being independent. So then we have that theta star. We draw a set of samples at time 0 of the prior at time 0 with respect to theta star, and then we run the particle filter with those M particles.
So you assume for the specific particle shapes and conditions.
Yes.
And after that, so I guess we go back to the assumption. I don't want to nitpick. It's just me trying to understand.
Mm-hmm. Back to the assumptions?
Yeah. And also nobody else asked the questions.
Yeah, well, that's so it's now your duty, although you don't.
It's probably uninteresting. Okay, so you've got that minorization constant.
This thing?
It's the same for all n, or it's different for different n?
Well, I'm saying, okay, fix n first,
Okay.
and then, yeah.
Okay.
Yeah, no, but
And
probably
then I guess
not.
The assumption on the cost is tied into A3 as well, right? Because the algorithm is going to get more costly, right?
This?
If you have more time.
Oh, yeah, C is probably going to depend on, well, C certainly depends on n, but actually that C probably depends on n as well. We haven't guaranteed that it doesn't.
So we know something about how particle MCMCs, how quickly it mixes. There's some sort of guidelines on how particle numbers should increase and stuff. So we took those loose guidelines. Has any of this been checked against those? Whether the numbers
The number of particles is taken to scale at least linear. The number of particles is taken to scale linearly with the number of observations. I think it's.
And that will fit the assumptions you, when you keep particle number scales linearly with observations, then your assumptions are fine. We can take it offline.
I think so, but actually, I don't think that we. I don't think that we checked that explicitly in verified it explicitly in the paper, but I think that. But we used the sort of rule of thumb from this stuff of Arno. Yeah.
Jeremy, you had a question?
Yeah.
So
Sorry.
I guess compared to the coupling that you talked about on Monday, this sort of approximate coupling approach is nice in the sense that you recover the rates that you wanted. But then aren't you also losing something in the sense that here you're doubling the space, right? So somehow the constants must depend more worse in dimension. I'm just saying, like, maybe there's the pros and cons there.
Yeah, by a factor of two. By a factor of two, probably. Yeah. Yeah. Well, yeah, but I mean, we're really more concerned about that losing half of the strong rate of convergence. At least, well, I mean, in all this stuff, anyways, it's asymptotic, right? So that there is always a question for practical application of the multi-level Monte Carlo stuff of what's the constant? Like even here, even for this case, there could be a epsilon for which actually it's more expensive. Actually, it's more expensive to get that epsilon for multi-level, but then. Right. I mean, we know that asymptotically, it's always going to be much better like that. So, yeah.